just to make sure. Okay, so just a little bit, I'm a little bit sorry. I will start with I'm in a different setting. So in case there is some loud noise in the middle, please like please allow for that thing. Fine. So we have been talking about neural networks, and the day one we started like how the inspiration for at least the single neuron was derived from biological neural networks, and then how a multi-layer perceptron or a neural network has been derived from combinations of those single perceptrons. In the second class, we touched on basically how weights are learned, how backpropagation works, and in the third class, we started looking at more of the techniques that are used to learn neural networks. We majorly approach this by finding what is the problem and then what is the solution, right? So we talked about gradient descent, we talked about batch gradient descent, and we talked about advantage and disadvantage. And then we moved on to stochastic gradient descent, how this solves the memory issue. But then stochastic leads to noisy gradients, basically. So it leads to a lot of the path to the optimal value becomes noisy, but of course it helps you in finding like specifically in non-convex landscape, how does it help you to find optimal? And but still this was not the best solution because it's noisy, and maybe there are too many iterations are required. So what do we do? So the best approach was basically the mini batch gradient descent, where we, instead of taking the full data set or a single, we take a set of data sets. And we discussed like 32 and 512 are like the min and the max, but that varies given what your data set is, what your neural network is, and so on. And of course, advantage is like efficient GPU computation, and mini batch gradient descent is the current general practice of doing things. Then we discuss like just because we did gradient descent doesn't mean we'll have answers. Maybe we are going very slow, maybe we're going fast, maybe we're jumping out. For that particular reason, momentum was added, right? So this was very nice input that was given. And this basically tells ki, okay, the next jump that you will take depends on whatever the past like velocity you had. Velocity is basically how much you have already accumulated in term of gradients. So it will depend on that. It's borrows from like physics notion. And we also discussed that classical momentum is fine, but you could do better by Nesterov's accelerated gradient. It basically says that instead of just looking at the past one time, what you can do is you can use the past, let go a little bit ahead, and then check, right? So it's a, like a look ahead gradient descent. So you're basically, instead of pulling the at the current position, what is the gradient? Instead of using that as a input, you are going a little bit ahead. That means your WT minus the lambda of VT minus 1, that basically tells the evaluation of the gradient. That means how far the current, what is the status of current gradient versus how much the previous baggage of gradients we have accumulated. uh, and generally it's like practical performance, but you can still, like, there are so many other methods too, but momentum works very fine. We basically get an accelerated approach to reach to the optimal. Yes, so gradient descent is super fine. Batch gradient descent, matlab, that is the original one, that works fine. But stochastic, but there are some issues with the memory. Stochastic has issue with let's say noisy. Mini batch is the current one, but only gradient descent won't solve. You need momentum, and only maybe classical momentum. If it does not work, then you can work for Nesterov accelerated gradient. Now, with all those, this also is not enough because the learning rate that you have is basically same for all the weights. Yes, or same for all the parameters, let's say. Yes, sometimes it's okay, but sometimes it's not okay because not all of the parameters are evaluated on each data set. So for example, let's say you are trying to find out, okay, so I'll give like image example. Like for example, you are trying to classify an image, let's say, right? So you're trying to identify if it is like a taxi or a regular car, right? So let's say there are some weights that are responsible finding regular, and the taxi, let's say it's like classical Kolkata taxi, let's say like yellow and black. Yes. So if you have such taxis, then if that comes very late, let's say after 50 images of regular cards, one such image comes. So for first 50 images, if you see, they're of regular colors, right? They're not with yellow, let's say, yellow color. So that means the parameters that were responsible for identifying those regular cars, they have been already having a very huge advantage of training. The moment it looks at yellow, that means you'd want it to accelerate in the direction of that yellow particular feature, so that the weights or the parameters that can be tagged with the yellow features of that image should be accelerated a little bit faster. That means the learning rate for it should be a little bit higher. So that was the exact notion behind having adaptive learning rates. So it's not that the every feature or every parameter has to be learned at the same rate. Any parameter that has been like frequently getting, let's say, these updates, you would rather have smaller updates for them, and anything that does not, you would rather have larger updates for them. So that was the reason behind like Adagrad. And then we came to Adam. Adam basically combines momentum as well as Adagrad. So it's basically says you can do momentum plus you can have per parameter learning rate. So basically, Adam is now the base standard optimizer that people use. So in case of your project as well as any paper you read, so they will tell like Adam optimizer using, they will specifically give what is the beta 1, beta 2 and epsilon values. So these are the ones that we have kept as default, but that does not mean this has to be taken across. If the question is like, how do we find what is the best value of beta 1 and beta 2 and epsilon? Basically start with the previous paper. Yes, whatever values they have taken, most likely they have tried or their previous paper have tried. Yes, most likely though, but you can, as a starting base, you can use whatever they have used and then take it forward. Hmm. So that's what like Adam Optimizer is, and currently most of the deep learning start task, at least to start with, they use Adam Optimizer. But then even with again gradient descent, momentum, then optimizer like the adaptive learning rate, which we landed with Adam, even with that, we still land up somehow with vanishing gradient. We talked about this vanishing gradient problem a little bit earlier also, especially when we discussed the activation functions, how they can lead to, for example, sigmoid. Towards the right end, it is closer to 1. Towards the left end of the curve, let's say it is like, or towards, let's say, negative values, it's closer to 0. Yes. So they basically, the gradients get squeezed towards the higher values or the very low values. Yeah. So that basically causes vanishing gradient, and there is another problem called exploding gradient as well. So here what happens is um the moment, so we have this momentum that gets built up, and and as we do this, if the gradient itself is super high, even if that multiplies the gradient that is below, let's say 0 point something, that can become really big, and that can technically go beyond the local minima. That means if you are in the curve, let's say zone, let's say, of the curve, so technically if you're here, it will straight jump to the next minima, let's say, which might not be even global. So this is still a problem that exists, and what we do is basically gradient clipping, better initialization, and skip connections. Yeah. We will talk about one or two gradient clipping. I talked, as in, doesn't matter what the gradient is, you clip it at 1.1. Yes, and we talked about this, like how 1.1 to the power this and 2 to the power number of deep letters is like very high, and so on. Now, then the task is basically overfitting and underfitting, bias variance trade-off. So the rest, all the things that we will talk about is basically how to tackle vanishing gradient and exploding gradient. Some of the problems will solve with Adam Optimizer, but there are still vanishing gradient and exploding gradient. Exploding gradient relies on gradient clipping as well as better initialization. So this better initialization is something that we will talk, and sometimes skip connection will talk also. Now, regularization technique, just to make sure this is complete. So we had L1 and L2 in the classical neural net, in the classical machine learning. And then here we have something called a dropout. In dropout, what we do, I have a nice figure. Unfortunately, I did not put it in this slide. I have in the next slide. I will show you there. What it does mean that if you have a neural network, some of the nodes are basically off for that particular round of training phase. I'll explain again, but I explained it yesterday, on the last class. So you randomly drop neurons during the training. You force the network to not rely on very specific neurons. It creates an ensemble effect because every time you train, there are some neurons that are out of the network. That means every time what you're training is a different neural network altogether. Yeah. As okay, so now dropout is one of the regulation because neural network. When you start with, you don't know how many number of neurons should be there. Yes, we will talk about that also in the one of the next class slide, but today's slide. And then the problem becomes like, okay, so is it too complex or is it not too complex? That question comes. And generally, when people pick up problems, they generally pick up a way larger neural network than it is actually required. Then basically, we try to regularize in some stuff that we try to reduce the number of parameters that are there. Yeah. And the next is basically weight initialization techniques. Yes. So one of the ways to solve, I told you, like uh, the issue of vanishing gradient, or let's say exploding gradient, is if you just start with the right weights, right, then the gradients need not come back to the first layer. Like if you have, let's say, 50 layer of neural network, so if it is vanishing, that means by the time you reach to the first layer from the 50th where the loss is calculated, it could either vanish or it could either explode. What if you just had the right weight initializations done? Yes, that though is like a secret recipe we might not have, but there are some ways to do this initialization properly. Yes, because bad initialization can also lead to issues. Yes, either it will make training impossible. If you have a vanishing gradient issue, then if the first two layers are important and you have made the initial weights really random, let's say very far away from the actual, then and the vanishing gradient problem happens, then those weights don't change, right? So it becomes impossible, and also it's slow because even if you want to change them, they will change at a very less rate. Yeah. So now what is the problem? Like if the inputs are too small, activation vanishes as you grow deeper. If the weights are too large, activations explode. Yes. So we need to choose initial weights that keep activation variance stable across layers. One of the ways is to Xavier insulation. Yes. So it was designed generally for sigmoid and tanh. Uh, then it was earlier very popular when sigmoid and tanh activations were rapidly used, and we talked about sigmoid and tanh already. And if you look at this, the variance is basically 2 over n in and n output. Yes, so n in is basically number of inputs, n out is number of outputs. Yeah, and so if you assume that there is a layer with 100 inputs and 50 outputs, then your like the variance would be like 2 by 50. Yes. Oh, 2 by, sorry, 150. 100 inputs plus 50, 2 by 150, that is 0.13. Yes. So with that, you could basically initialize your weights, or otherwise you could have uniform. So you can sample from uniform distribution. There is a formula given like 6 over n in and n out and root over. And both like Gaussian and uniform versions will work fine. Xavier is Gaussian, but it's like a different variance, and then or with a particular variance. So both Gaussian and like this uniform versions, they work well. Yes, and specifically they were designed for sigmoid and tanh. And what is the next? So next came basically the uh, okay, so just to make sure the things are clear, so like around 2010 probably this initialization came into picture most likely. Training deep neural networks also very difficult. Like what do we start with? What should be the initial weight? This was a very simple idea. Okay, let's use normal distribution to do that and Gaussian, and then sure, it worked fine. And but the next is like ReLU came into the picture where it was a much more simpler activation layer, but then what we need to do? Yes. So the problem, not the problem, let's say the feature of ReLU was it basically any negative value becomes a zero. So basically it effectively kills half of the neurons. These halves basically, it basically makes half of the variance also, right? Variance of activations. So he initialization basically says that, and then it just basically tells that, okay, you can use this formula like normal with the variance of sigma by 2, but it does not depend upon output as such. But we can just do 2 over n. Yes. Uh, s- uh, this is just like just to maintain the activation variance, and the factor of 2 basically compensates the ReLU killing half of the neurons. Yes. And so the rule of thumb is very simple. So if you have a sigmoid or a tanh activation, just use Xavier. If you have he initialization, matlab ReLU or leaky ReLU, just use he initialization. Yes. Fine. And if you use like, do you have to calculate every time all this? No. So if you use a proper framework, let's say PyTorch or TensorFlow and any other library, let's say, uh, they will technically have this already inbuilt. It will be just like calling another function. Yes, like the scikit-learn model dot fit, the way you call. PyTorch has nn dot init dot Xavier underscore normal as a function. Yes, that will work fine. Yeah. And hey initialization will be chiming hey, so it will be underscore like underscore chiming. Yeah, so that you can use. So trying to wrap up that particular like last class most likely. So what we want to say that the learning rate is probably one of the most important hyperparameters, and learning rates like scheduling is can also be done. So we have discussed a lot on learning rate by momentum. No, momentum does not. So adaptive learning rates, ADAM and ADAGRAD we used. There are some other things that you can also do. So one of them is called step decay. Yes, these are all very important in the terms of whenever you have a very deep network or a very large network. Yes, all this come into picture. If you don't use any one of them, or if you miss some of them, okay, you might not able to be match the accuracy, right? So that should not drop your faith in neural networks. It's just that probably there are some newer techniques that should be used to make sure that you reach to higher accuracies. Yes. So one of them is step decay. It's basically you reduce the learning rate by a factor of gamma, let's say every some number of epochs. Epochs, I hope you remember, epochs is the like total number of iterations to cover the entire data set. Yes. But one epoch is that, and you do it after every like some number of epochs, you can reduce the learning rate. It's very simple. Yes. And then basically you can divide it by 10 of every 30 epochs. That could be like a small example. Yes, it's very easy to understand, very easy to implement as well, no issues. Then there is called exponential decay. It's same again, the learning rate is getting decaying, but with a like a smooth and a very continuous decay rather than a divide by 10. Yeah. So it's a more gradual drop, you know, step decay. Yes. Then compared to the step decay. So it's very common in older papers, but not now. Exponential decay, I don't know, not used that much. Cosine annealing, very nice. So learning rate follows like a cosine curve from like eta max down to eta mean. Yes, it's a smooth and gradual also, and it's a little bit popular nowadays. It's popular. Yes, exponential decay, step decay, not used that much. Cosine annealing is what is preferred, and is often specifically what you do is, I don't know if you have seen papers. Maybe if you have started reading papers on neural networks on material sciences, let's say they will also do like technically once you start decaying the learning rate at one time, you will also restart. That means, let's say learning rate started with, let's say, 10 to the power minus 1, it will start decay 10 to the power minus, let's say, 6, and then again you take it to 10 to the power minus 1 and again. Yes, so there is a sometimes called a restarts we do. Yes, so it is often used with the restarts, and where we jump back to the eta max. Yes, so we do that periodically. This is also nice learning rate warm up. If you see previous papers using it, just use it. This follows from other potential works. So we start with a very small learning rate and then gradually increase. Yes. Why we do this? So this is basically opposite of step decay, exponential decay, and cosine decay. Because early in training, what we see is basically what if they are super noisy? Like the gradients itself will be super noisy, right? Because the gradients are getting back propagated, and whatever the gradients you are calculating are because of these noisy weights. So that means the gradients itself are like might be super noisy. Either the data set is noisy or the weights are noisy. So the gradient itself will be noisy. So you don't want to change at a very rapid rate in the beginning. Yes. That's how warm up helps. So it will prevent taking very random steps in the beginning. So what we can do is, if you want to train like for 100 epochs, then like for 5 to 10 epochs, maybe you first do a warm up, and then you can do the cosine annealing or any decay method that you can use. And definitely, like any adaptive optimizers that you have, let's say Adam, anything that you have, technically they will come up with all this learning rate if you will see them in the code and in the paper when you read them. Yeah. What is the best strategy? There is no best strategy for now. Like there is a practice strategy which we can tell. So you can start with a random learning rate for a few uh, like epochs. Does the model train? How do you know the model train? The loss has to decrease. So you have to add a warm up for 5 to 10 epochs. Then you add cosine annealing or step decay and use adder. Okay. Hopefully that will work fine. The next one I'm iterating here, but I also iterate later. There is another thing called batch normalization. Uh, I'll just go over it. I will again repeat in the next slide. So batch normalization basically tells I think it came into picture around 2015, and nowadays everybody uses batch normalization, but everybody now has also moved on in terms of normalization. Like batch might not be super popular now. But what it says, I think you can see the equations and all, but I will just say, so the what we do is basically uh, is the same thing. If we go back, you remember the cricket thing, like the salary versus the age thing. Like the difference in the age will be very less, but the difference between salary can be very high. But the difference in salary is very high, that the difference being very high or the value being very high itself uh, can impact, right? Because that will just play the bigger role. The weight associated with the salary will just play a bigger role because the numbers associated with salary are way higher compared to age. Then the point is, what if the answer actually depended on age? You will just spend a lot of time in finding the correct weight for the salary, right? So either it will be bad training or you cannot train at all, right? So that's why normalization was introduced. Now normalization, you don't need to do it across the data set in the beginning. So what you can do is you can do it per mini batch. That means a mini batch, I hope you understand. Batch is the entire data set. Stochastic gradient descent contains only one. Mini batch would be a set of those. In the entire batch of 100, let's say 10 is the set of samples that we are going to train our model on. That means we calculate gradients across each of those 10 samples, we combine them, then only we do a backpropagation, not with every sample that we get. Now, for the current mini batch, you compute the mean and variance. Once you compute per feature across batch dimension, right? So if you have 32 examples, for example, let's say if you have 32 examples with 64 features, you compute 64 means and 64 variances. Yes, this is across all the features. Yeah. Now, how do you, when across all features, when the per feature you do, yeah. My bad if across meant other way. Now you subtract the mean, you do the same normalization technique, you subtract the mean, divide by standard deviation. Uh, then the values basically become normalized between, like that will have mean of 0 and variance of 1. It's like general standardization. Yes. And then the other thing that we have is called scale and shift. It looks uh, like different from general omission, but that is the clever part basically. You can introduce learnable parameters called gamma and beta. Yes, that is the scale and shift. Here the network can basically learn to undo the normalization if needed, right? So basically if gamma is basically, let's say, sigma square plus epsilon's root over, and beta if is equal to mu. uh, Even if you start, let's say, reducing or decreasing the values using the mean and variance, beta and gamma, basically we can learn beta and gamma so that if the normalization actually hampered the learning, this can help us going back to the original. Yeah. So, but the idea is basically instead of just relying on batch normalization and the mean and the variance in that particular batch, we can have two additional parameters that we can learn. Yes. Otherwise, what will happen is always the activations will always have the mean of 0 and variance as 1. Yes. What if the optimal distribution is separate? What if the optimal distribution has a different mean and different variance, right? Then either we will not learn or finding that will be very, very hard. Yes. So that is the basically advantage that we get from having this gamma and beta. Yeah. Fine. Where the normalization is generally applied, normalization is generally applied uh, after the linear transformation, but before activation. That means after you do this W1 X1, W2 X2, W3 X3 from all the neurons, we gather the information. Before sending it to a sigmoid, tanh, or ReLU, you do a normalization and then you send it. Yes. So typically it becomes input, then you do that linear transformation of W and X, you do a batch norm, and then you do an activation. Right? Uh, Again, so you might not actually do all these things. It will come with the standard set of practices, but please remember, if you're having some issues, probably this can help. Yeah? And so why does batch normalization helps basically? Batch normalization is one of those techniques basically where original explanation itself wasn't right. Yes. Uh, basically we thought ki batch normalization should have worked in this way because we're normalizing between 0 and 1. That variance, that larger values won't help. Um, but the original paper that introduced it, they introduced it as if it reduces the internal covariate shift. Yes, the change in the input layer distributions. Yeah. That means if the layer inputs keep on changing, that means every batch sees a different value of the features, then it will be harder for later layers to adapt. Batch normalization basically will try to dampen. So, for example, the first 10 examples that you saw had like salaries of, let's say, 100,000. The next, next 10 examples that you will see in the next epoch or next mini batch, they will have salary of, let's say, 100. It becomes very hard to train that way. Here it is, everything is between 0 and 1. Yes. So, but what exactly happens is basically the regularization effect comes into picture when batch normalization is implemented. Batch normalization basically adds noise because each example is normalized. Okay, using batch statistics, not its own. So that means whatever mean and variance you are calculating mean and variance within that particular batch rather than the entire data set. If you calculate across the entire data set, then it would have been better. But calculating that is also time consuming, let's say. But if we do it within the batch statistics itself, like the mini batch, that adds some level of noise. This noise itself, that basically noise per mini batch, it acts as a regularization. Yes? Basically, it says, okay, whatever we see, it's closer to what we want, but there is some level of perturbation. Yes, that is what generalization means. If you remember to the first class I told, memorization is basically remembering everything. And let's say like the oracle mode is answering everything, doesn't matter what you know. But the middle path is what we want. The generalization is what we want. So we don't want to remember everything that is in memory. To make sure this happens, once we do this mini batch normalization, the mini batch normalization adds some level of noise. The mean and the variance is calculated per that mini batch. Yeah. And that basically helps us not to memorize this particular batch, rather memorize a little bit different with the added noise. Yes, not memorize per se, but generalization. Yes. And also gradient flow, like batch normalization will definitely help with because first of all, the optimization landscape itself is smoother. Loss surface will become sensitive to parameter installation, and gradients will be much better behaved because the values are between 0 and 1. Yes. And this will also allow us to have very high learning rates generally. Hmm. Uh, And typically, what we can do is, because we can use batch normalization, we can use very high learning rates, so that if we use high learning rates, then we can train also faster. Yeah, fine. Excellent. So now, mostly ending. Yeah. Uh, Generally, this training loss, if you have this curve, generally whatever like scikit-learn or the PyTorch or TensorFlow, generally you will be plotting this training loss curve. Basically, with the iterations, how your loss is going. Generally, if the loss decreases, you understand model is learning. Now, validation loss is something that I hope you remember training, validation, testing. If the validation loss starts increasing, then you have overfitting issue. Yes. So training loss is like this. Validation loss should also be like this. But if validation loss starts increasing, then it becomes overfitting. And now, if both losses plateau, then of course, and if it is not like low enough, then probably either we have to increase the strength or the capacity of the network. That means you add more neurons either in depth or in the height, or you have a like a completely different architecture. Maybe whatever you have done with the simple neural networks is just not enough. You can also like monitor the gradient. Is it vanishing? Is it too large? Are the weights getting updated or not? Yes. And then parameter updates, at least they should get updated. Then activation statistics also, mean activation should not be zero, and all or saturated. Activation variant, they should remain all stable, right? So that means after activation, it should not, all the things should not be continuously giving zeros. That means those neurons are not getting used. Either you should use dropouts and other things to make sure those neurons get activated, or it should not always also tell you, okay, if it was like tanh or this one, always one or minus one. Yes. So then that will be also an issue. Uh, Again, so just to summarize, we have gradient descent variants, batch, mini batch, momentum, and Nesterov is there. Adaptive methods, Adagrad and Adam, vanishing gradients, exploding gradients, overfitting. We also talked about initialization and regulation. Yes, in a network. Fine. I have the notebook for it, but I will show you probably Monday only. Today we will jump to continuation of this. Okay. I hope that is visible. I could not witness PDF thing is not here. Okay. Fine. This is like we are just following up. Some of the things if might look a little bit difficult, but I just want you to remember some parts of it so that you can just come back to it and does not look very novel. Yes. Sorry, I keep repeating this statement because some of the parts I know, like you'll probably never see maybe, but most of the papers nowadays, if you read anything beyond 22, 23, 24, 25 papers, they will have all these terms ready. Yeah. So what we do next? Okay, fine. So in this particular class, what we want to do is we want to explore a little bit more into advanced architectures that we have and regulation techniques. All these are, how do I say it? These are advanced. Probably, if I had have taught, let's say 5 years ago, I would have still called them advanced. Now it will be regular. Any paper that you see, it will be there. So now let's go ahead. Huh? Sorry. Yeah. Just to give an intuition, these figures are added in the previous slide. Somehow they're not popping up. Fine. So this is how a neural network looks like. Yes. So you have an input layer, you have a hidden layer, and you have an output layer. There are a bunch of variations on this. I'm not going there yet right now, but this is how it looks like, right? So input, anything that is in between that is hidden, output is there. All these edges that you see, they are all weights. Yes. And typically when backpropagation happens, you come from the output layer to the input layer. Okay, through these weights only. Yes. And all the lines basically that are going on from one node to another, they're basically, this node is giving input to the next node. Yes. And it is weighted. So you apply linear normalization, then the activation function. Yes. I hope that is fine. That gives a notion. Yeah. Now one of the like most fundamental question that is affecting like all ML and all deep learning, and also it will affect you also. Yes, because you'll be using these tools. Yes. So like, should we build it like more in depth or more in width, right? So assume depth is basically adding more hidden layers. Width will be basically increasing the number of neurons in each hidden layer. Yes, I hope depth is more hidden layers, width is more neurons in a single layer. So now this is the question, like, what do we do? Now, the classical universal approximation theorem that we had discussed, that basically told ki if we have a single layer, single hidden layer with enough neurons, right? We had input, one hidden layer, one output. Sorry. And if the single hidden layer itself has enough number of neurons, then it can approximate any continuous function. That's what universal approximation theorem says. Of course, super great. But the problem is like how many neurons and so on and so forth is there. But the modern understanding says, like nowadays, it's basically that depth is what provides an exponential advantage. Basically, deeper networks can represent certain functions exponentially more efficiently, right? Both will work, but it's just that deeper like anything deeper network will basically do it with less number of neurons, let's say. Yeah. And if it is not deep, it is otherwise it's called a shallow, right? Shallow network. So you can think of trying to create a very complex structure in the beginning, or you use, let's say, Lego blocks if you have like the one that you put on top of each other and make a bigger thing. Yes, Lego thing is more into like deeply with the depth. Yeah. So what we say that you can represent this complex structures more efficiently by stacking layers, yeah, than by building one massive layer. That's what it says. So a function with basically k layers, yeah, and n neurons per layer will require only, let's say, k times n squared parameters, right? Uh, and like, but for the same function with just one layer, let's say, could require around n to the power k parameters. Of course, like n to the power k is way bigger than k times n squared. So that's basically the exponential advantage versus the polynomial growth, let's say. Yeah. Sorry, exponential disadvantage versus the polynomial growth. Now, an addition to this is basically the abstraction that comes with it. So basically, each layer will learn hierarchical features. Each layer will learn some portion of the final answer. So typically, we don't see the exact behavior. Like some probable behavior we have seen with, let's say, images. Like early layers will detect edges, middle layers will detect shapes, and the final deep layer will detect objects. So the few layers, primitive features, middle layers, some more like more little bit complicated features, and the final layers will deal with more complicated features. Yes. But and hierarchical learning is one of the most efficient, more computationally efficient learning, let's say. Yeah. But then it does not come with. We understand now deeper is efficient. Like anything that is with depth is efficient, but problems. Yes. One of the bigger problems is when you increase the number of layers, as we discussed, vanishing gradient, right? The gradients while coming to the first layer, they will basically either be zero or like close to zero. Yes. Uh, so now whenever we try to backpropagate through L number of layers, we are basically computing L terms, right? So this product of L terms, and if it is less than zero, we have discussed this, we'll basically get zero. Now, what do we do with this? So one of the ways to tackle this was basically residual connections. So mathematical formula is very simple. What we do is basically instead of computing like a layer plus one, uh, so this particular AL, let's say, what we do is rather we compute like the variance of A layer plus the F of, let's say, A layer. Yes. Uh, it basically says like, can we have a like a some residual block that has been given, like the original A, can it come back? Yes. I'll show you in a figure in a bit. Yes. So here what we do is basically we are just adding the input directly to the learned residual. Fine. So whatever learning that has happened, if it becomes very small, we can bring back the again the input, like the gradient can again, we can have a bigger input come back, but it's not shown as a gradient input, but rather in a residual the input goes to the front. That means by the time, let's say you gave it a picture of cat, and by the time it reaches here it only understands, let's say, edges and circles. Yes, that's not enough. So you again bring back the input, like this is a cat, all the features you give it back to somewhere in the middle. Yes. So that's what the residual connection says. And the gradient flow is also simple. It's just that you have to calculate, um, the gradient will flow in like two channels. I will show you one figure in some time. Uh, so like earlier, what used to happen, the derivative used to become zero. Now that we have given an input channel, the derivative will at least have some value. That is the entire thing. Yes. Uh, so what is happening is basically residual networks work fine. We have, if you have heard about the terms of ResNet, they build on this residual networks. Yes. And this prevents the vanishing gradient. The next is basically the skip connections, right? This basically, they have been inspired by this residual connections only. There are just two variants. One of them is like dense net or dense networks, let's say. What we say is that instead of just adding one layer, what if we concatenate all the previous layers? I will just maybe, yeah. So skip connection looks like this, right? So for example, let's say if you have this particular figure, layer 1 and layer 2, assume layer 1 meaning that it has a number of neurons, layer 2 has number of neurons, but currently we don't care. So generally X goes to layer 1, and then you get an output, you pass it through activation, and then you send it to layer 2. Yes. So here what we do, um, along with that information that is getting passing, we also move the input back to the front. Yes. And we do an addition. Fine. So this is what a skip connection looks like. This is an identity skip connection because we're exactly adding X. There can be other variants. One of the variants was basically the dense connections. I told you dense connection is basically, instead of just moving X, what you do is you add the current X and the previous X. That means if I added, let's say, the AX, this activation plus the previous X, and we made it added to the previous one, that means instead of just adding the X, we added X minus 1 and X minus 2 and X minus 3. If all those are concatenated and we add. So those are called dense nets. Yes. Uh, this also like, how do I say, this helps us in reusing the features, but again this will add to a lot more memory also. Yes. And the other thing is basically called the highway networks, and this one also uh, does residual connection, but here what we have is something called a learnable gate. Yes. Here the information passes again from X. In the original residual connection, if you look at it, it's just a direct addition, right? We don't have any control how much information is coming from the behind. Maybe all of the information was not required. Yes. Or maybe some portion, like some magnitude of alteration is required. Now that is basically done through this highway networks. So basically we are saying there are learnable gates. Gates are basically, I like, you all come from physics, probably, like gates are okay. So gates are basically, they are used to control the information flow. Basically, you can assume that's a weight. Yes. And we have a transform gate, let's say like a T is there, and then it learns how much of the transform features to use. That means the original A that we are moving forward, we just add T in top of it. So it basically tells how much we have to move it forward. Yeah. And there can be many types of gates also, like you will see in other networks. I'm not saying like when it comes, when we discuss papers like that, you will see that. Yeah. And just to go back to one of the previous things, like we had dropout. I'm just repeating it here because I had the picture here. So dropout is, again, I told you, like parts of the neural network is basically held out, and it gets trained. So I'll just explain it through the figure. So I hope you can see this one. This is the basically the left hand side is the neural network, and the moment you do drop out, few of the neurons are out of the network, right? So uh, here the idea is basically like instead of making sure like here instead of making sure that uh, only a few neurons in the network learn, because that might happen. What you allow is basically every time if you start dropping randomly the neurons and you train the network again, you're basically saying, okay, you know what? If all the neurons are important, please try to make sure that whenever you try to answer it correctly, it can also follow another path and answer it correctly. Yes, that is all it wants to say. And every time we do training, that means every time there is an, how do I say, let's say each iteration, let's say iteration is where you do a update of the network. Every time you do a random dropout, like in this particular phase, these are the neurons dropout. In the next iteration, when you train for that particular another mini batch, let's say, you can have a different configuration of the network, right? And as I told you, like this also introduces this, like every time you are training a different neural network, so this becomes a more like an ensemble learning. Yes. Because every time it is a new network. In, I hope you remember ensemble learning, for example, random forest, where each of the decision trees were trained on a different set of bags. Yes, and each bag contained a, like, bootstrapped samples. Yes. So here also similarly, the bootstrapped samples we don't have, but at least this kind of like uh, at least uh, uh, dropout as a regularizer can be used. And every time ensemble, like each becomes a new neural network, so it becomes like an ensemble. Yes. So this is one of the technique to make sure that your network either does not overfit as well as the entire network gets used and we become more generalized. Yes. Because, and you have to remember, I repeated it last time also, during testing, you have to make sure that the dropout is dropped, right? You want the entire network to be used. And there are many types of dropouts as well. Like you can have standard dropout, special dropout, and drop connect. All these vary in some form or the other on how to choose, like what to choose, first of all. Like for example, special dropout is like once we reach to CNNs, I'll cover that. Now what you can do is instead of dropping neurons, you can drop edges also, like what weights to drop. That can also be done. That is basically drop connect. Yes. So you can drop neurons, you can drop special dropout. I'll talk when I reach CNNs. And this is drop connect, where we, instead of dropping neurons, we drop the edges. Fine. The next one is early stopping, but I will also do a early stop here today at like 5:20. Otherwise, it will become too heavy maybe. From here, we'll start. I will show you the code on Monday. But if there are any other questions, please let me know. Any particular thing that can be like repeated, I will try to just combine. But I hope you are getting the feeling, like, because neural network is just, there are that's how the major research has been done for last like at least 10 good years now. More than that, but 10 good years is where all of these new things that have come, like most of the things that we are telling is majorly last 10 years. Decay and all this stuff recent. Okay, 20 momentum maybe like 2010, sure. Yeah. uh, I hope like things are getting passed too, and whenever you hear these terms, okay, I recall now why this is important and why should we also have it. Yeah. Okay, any questions if they're there? And another reminder for credit student, your midterm is due yesterday. So uh, hopefully you submit it at best if you're not by this weekend. Yeah, Professor, I'm done for today, at least for the lecture part.
Okay,
If anything,
that is fine. Again, I would repeat what you just said. Credit students should submit their midterms, and yeah. Um, so we'll continue on Monday, right?
yeah, Monday 4:30. I will see you all. Yes.
Fine.
Yeah. Okay.
I-
Fine. All.
Okay.
Yes. Yeah.